students. Now in today's video we will do the discussion on the topic magnetic field due to the infinite plane sheet, due to the solenoid and due to the toroid. So first of all I am going to find the field due to infinite plane sheet. Then see this. Let's suppose this is an infinite plane sheet. Looks like your resistor in which you are making the notes. Okay, so this is called its front side and this is the opposite into the board. If I have a resistor, if I insert the resistor inside this board, then how it looks like? It looks like this. And if current is passing from this end to the board, then you can draw it like a cross. That means the current is going inside. If the current is going inside, then what would be the direction of the magnetic field? Would be in clockwise direction. So I will draw the magnetic line of force tangentially. So it is the upper portion of the magnetic field and it is the bottom portion of the magnetic field. And the magnetic field strength is denoted by the B. Okay. Now see, if I insert one square lamina inside the magnetic field, a square lamina, a square loop having number of turns and carry current I and has the side length L. So this is called the current. Name is A, B, C, D. Okay. And the side is called the L, so I will draw here the L. So the current passing through per unit length is called the current density. So I will write here magnetic field is the B, vector B, the current is called the I, the side length is the L. Then you will write here current density, passive, that means the current density, current present in per unit length, they are current passing through per unit length. J is equal to I by L. Then how you can find the current? The current would be I is equal to J dot L. Okay, so this is your equation number first. Now, how you will find the magnetic field of this plane sheet? By applying Ampere's circuital law. Okay, now you have to see the Ampere's circuital law application here. Then line irrigation vector B dot vector DL always equal to the mu naught times then the I. But vector B dot vector DL, DL is the small element here, the one side you can say. So there are four sides, so you can say the L as the DL, right? But the line irrigation is telling you have to count entire side. So I will write this portion. Now, if the current starts from A and ended up to the A, then you have to convert this form into the four fragment. So I will write here vector B line irrigation from A to B. I am converting it into this magnetic field as vector B dot. A to B has length L, so I will write here the vector L plus the next portion. The current is moving here from the B to C, so I have to integrate here. Then it starts from B and ended up to the C. Then BC, vector B dot, the side again is the L. Plus, here is CD. The current is going from C to D. So I'll write here CD, vector B dot vector L plus DA. So the DA, vector B dot vector L. And which is equal to mu naught I. So I will write here the capital I. Now, take a look. The dot product is telling the angle between B and L always in a cos theta form. If the B is here and AB has direction, so the side L is parallel to the B. Here the angle between the B and L is the 0 degree. So at the 0 degree, cos 0 degree is equal to 1. So its value will come like BL plus the B dot L at BC. B to C is making 90 degree with the field. So at 90 degree the cos becomes 0. So it becomes the 0. So I am not writing 0. Again, CD. Now the CD. In this time the magnetic field going here. And the CD has direction here. Again they are parallel. So it becomes the BL again. And the DA is perpendicular to the field, becomes 0, and which is equal to the mu naught I. Right. BL 2BL is equal to mu naught I. So the B is equal to mu naught I by 2L. This is the magnetic field due to the plane sheet. And if number of turns is n, then mu naught I by 2n. Okay? Please note it down. Now our next topic is the solenoid. See, a solenoid is the a structure in which we take a long current carrying conductor in Halaxian form with number of turns in per unit length. So this is your solenoid's diagram. I have taken the long wire and I have made it in a halaxial form. So its length increases and this is called its diameter. A solenoid is a structure in which the length of the solenoid is very large as compared to the diameter. So half of the diameter you can calculate the radius of its halaxial rings. Okay. So how to find the magnetic field of it? Now I am going to draw the diagram again here. You can note it down. Let's suppose this is the solid core. Okay. And the wire is coming from this side and going inside, going back, coming to the front, going back, coming to the front and again going back, coming to the front and again going back, coming, going, and this is the other side of the wire. It's called the one end, it's called the other end. If I connect with the battery and the key and on pressing the key, the current begins to flow. So the current flows like this, going, inserting into the board, comes out from the board and again passing like this. Okay, so these 2 points are very important. At this point, the current is going inside. If it is going inside, so at this point I have to show the cross. This is the cross for the current, not for the magnetic field. And when it comes out from the board, so you have to show, if it is coming like, you have to show the dot. Okay, again it is going inside, so at this point you have to show the cross, and if it is coming out, you have to show the dot here. Again the cross, at this point dot, the cross, the dot, and the cross. So one more time you have to show the dot here. Right? So what is the meaning of the crossing and dot? The cross is telling the current is going inside and the dots are telling the current comes out. Okay. Now these cross here and these dots are here. Okay. And this is the magnet, the current carrying conductor. I'll draw like this. Okay, so current is going like that. So you can imagine this solenoid here. So at this point when it is going inside, so the direction of the magnetic field would be in which manner? It would be in this clockwise direction. So you will draw here some clockwise circle. Clockwise circle. Closed. Clockwise circle. Closed. Like. And all have the same direction. If it is coming out, then you will draw the this anti-clockwise direction. So I will draw like don't attach these circles. as this direction. You can do like this here. Okay. Now you can see it is coming and going in this direction from this side, and it is going in this side. So overall magnetic field line you can draw like this. And overall magnetic field due to this side you will draw like this. Because as we know, the magnetic field line never intersect to each other, so they repulse in such a way. So this is called its direction going there. This is called its direction in coming here. So finally the magnetic field lines will go in this direction. But there is one line which always be parallel. Yes, called the central line passing through the axis of the solenoid. So here is the diagram of magnetic field due to the solenoid. The magnetic field going from this direction to that direction. This is called its south pole and this is called its north pole. Right? And the direction of the magnetic field which I have denoted, it comes inside of the solenoid. Right? How to find the magnetic field due to the solenoid? Do one thing. You can imagine the point number 1. This is called the length of the this solenoid. This is the length of the solenoid. Okay. And the number of turns total called the N. Its number of turns in per unit length denoted by the small n. So I can write the capital N is equal to small n dot n. Right? Let's suppose I have inserted one plain lamina inside it. It's called as the square loop. So square loop I will draw with other chalk. So this is the square loop here. Square loop of side L. Right? So it has the 4 sides A, B, C and called the D, and having the length L. Current passes through, it's called the I. Right? I, and its length is the L. So again you can see here the magnetic field is here, not outside from the solenoid. So at this point, at this side, the magnetic field would be 0. So I will write outside from the solenoid, the magnetic field would be 0. And at this side, the magnetic field is perpendicular. So the magnetic field would be 0 again here. The magnetic field would be 0 again here. You can calculate the magnetic field only in this side for the AC. So see this, outside from the solenoid there is no magnetic field. At this side and at this side they are the perpendicular, the magnetic field becomes 0. And at this side the AC, from C to A, so this is CD, yes. At the CD the magnetic field would be parallel to the length. So you can calculate the magnetic field only for the CD. So I am going to calculate here by taking Ampere's law. So I am writing Ampere's law. Line irrigation from C to D only. C to D, vector B dot vector DL is equal to mu naught I. And I told you the number of turns is the capital N. Okay, so I can write here C to D, vector B. Oh, you do one thing. So the vector P and the CD to DL, CCD the length kitni hai? That's called the L. And they are the parallel. The cos 0 is 1, then B dot L is equal to mu naught. And if the current is in per unit length is the capital N, so I can write here I, where the N is the total number of turns of the loop, and this B is equal to mu 0 capital N I by L, and this capital N has value small nl. You will write v0 nl dot I by L. So these L cancels. So B is equal to mu 0 Ni left. So this is magnetic field due to the solenoid, right? Do this. Now our next, this last topic is the toroid. Next and last we can say. So toroid is a endless solenoid come in a closed ring. That's why it is called the endless solenoid. And what would be the diagram of the solenoid? This toroid is, say, this is the circular core. I'm not good in a diagram. So this is called a circular core. Circular core of the thickness like this. And if I rotate the wire from this end, like by rotating the wire in the heliaxial form, wrapping the wire on the core, so it comes like this. It has no starting point, it has no ending point. That is called the endless solenoid. So this is called the one end of the wire and this is called the other end of the wire. It has a closed shape and the shape of the rings is not in an actual circular manner. They are the heliaxial in shape. And this point you can connect with the battery and the key. So this is called the toroid. Right? Toroid has different radius. It's called the radius R1 from the center O. This is called the radius R2 from the center. That means the internal and the external. What will happen when we pass the current through this solenoid? When I make it on, see, the current begins to flow. So the current begins to flow from this end, going inside and it comes out like this. So I'm drawing here. Yes, it is coming here. Okay. But what would happen when the current passes through this toroid? So what would be the shape and the structure of the magnetic field? So see here. This is the center and this is called the internal ring of the solenoid of radius R1. So the magnetic field will develop at this radius also. Right? This is called the external radius R2. So I will draw here. थोड़ा सा यहाँ बिगड़ गया. As I told you, I'm not good in a diagram how to draw it. चलो काम चल जाएगा. Okay, so this is called the R1, 0. It's called the, so not the 0, it's called the O, and this is the R2. Now at this point, if the toroid is like this, so the current is coming out. यहाँ पे आप ध्यान से देखो, हर एक सर्कल की रिंग पे ध्यान देखो. अगर आप सपोज यहाँ देखोगे कि करंट जा रहा है, इस पॉइंट पे आप देखो या किसी भी पॉइंट पे इनसाइड देखो, करंट यहाँ से घुस करके यहाँ निकल रहा है. The current is coming out from inside. So at these point you have to draw the dots. That means जो भी वायर्स होंगी यहाँ पर उनसे करंट बाहर की तरफ आ रहा है, out from the board. Okay, right. And the current is going inside the board at this end, this end, this end. So you have to draw here the crosses. I will draw the cross as I draw the dots in front of them face to face. Okay, so it takes time. to draw, right? Okay, so this is called the current is going inside and coming out. So the going inside and coming out. So this is called the direction of the current. But the magnetic field will develop in which manner? See, so this is called the current is going inside. So the magnetic field will be in a clockwise direction. At here, the magnetic field would be in a this anti-clockwise direction. Okay. So at this point, I will draw only the two rings here. One is here, I will draw at here, and one is here. For the magnetic field at this point, so I can denote it. The magnetic field will develop in a clockwise direction. So this is called the magnetic field ring, and this is called the other direction. So I will draw here. The magnetic field is coming out, so this is called the anti-clockwise direction. Okay. So you can denote it as with the direction clockwise. So it is here, here, and here. Good. And this is called the anti-clockwise. So you can denote it like here, like okay. But these two circles, they are passing the current inside the toroid in the same way, in the same direction. Okay. So you can write this is called the resultant tangential direction of the magnetic field. But the magnetic field cannot go out from the ring, so it always moves in this way, in a ring form. थोड़ा सा सही तरीके से ड्रॉ करना होगा. So everywhere the magnetic field will develop, and the magnetic field's ring would be the dark white line. This is called the resultant direction of the magnetic field inside the toroid. Okay. Inside the solenoid and inside the toroid, and on its axis, the magnetic field would be maximum. And outside there is no magnetic field. But in the idle solenoid and in the idle toroid, the magnetic field exists outside also, but for only the limited reason. Okay, so you can see here, this is called the magnetic field, resultant magnetic field inside the toroid, and the axis of this magnetic field, which is called the central axis of the ring, has the radius r. Okay, and if you want to take the small element up to this region, if I took the small element here, has the length dl, vector called the dl, and the magnetic field is going vector b up, so these two directions would be same, and the cos will be the 0 degree. So at each and every point you can find the magnetic field, and the magnetic field you can find with the same process as I did in the solenoid. So the magnetic field will be B is equal to mu 0 and I, where n is called the number of turns in per unit length and I is the current, mu 0 is the permeability, right? So this is called the solenoid, the toroid. One more thing is, you have to note it down, inside this toroid there is no magnetic field, because the current is going and passing inside into the board, so the magnetic field will develop here and here. No magnetic field will develop at the center. So at the center the magnetic field would be 0, at outside the magnetic field would be 0, the magnetic field would be maximum here, right? Note it down please. Thank you.